Before we jump into the next topic, there is a photograph I forgot to show you, and here it is. This is another Earth from space photograph, and the thing that I want you to pay attention to is this hazy thing right here at the edge. Whoops, won't let me write an edge. Okay. As you can see, we're looking down on the planet. There's a bunch of clouds in this region here, but that's not the thing that we're most interested in. It's this thin haze at the edge. That's the atmosphere, and what I want you to all appreciate is that's all we have. That's it between us at the surface and the cold vacuum of outer space. We're going to spend a lot of time in this class learning the structure of this thing and how it works, but it's useful to see a photograph of it to see just exactly how tenuous the whole thing is. Okay, let's go back to our lectures and let's start looking at one of these spheres, and we're going to look at the oceans, and that's part of the hydrosphere, of course. So let's write down a few facts about the ocean, and these are from chapter 2 in the book. 72% of our planet is covered by ocean, so of course we think that the oceans are very important. There's enough water to cover the planet to a layer 2.6 kilometers deep. Now, I don't know about you, but I find that amazing. 2.6 kilometers deep. That's a lot of water. But of course, most of it is salty and so difficult to get at for drinking and so forth. The oceans are salty. And there's a couple of things about salt water that are important to pay attention to, because this ends up having an impact on driving our atmosphere's circulation, and the climate. The ocean water is salty, and it turns out that salt water is more dense than fresh water. So if you imagine, let's get a little pen going here. If you imagine a column of ocean water, here's the surface of the ocean, and if you imagine a column of water down to the bottom, then the salty water is going to sink to the bottom because it's denser and heavier, whereas the fresh or fresher water is going to stay at the top of the ocean because it's less dense. We'll see why that matters in a minute. Here's a number to remember. On average, 35 grams of salt for every kilogram of fresh water. It varies, but that's a nice number to just remember. What else have we got here? Something to remember about fresh water is that it is most dense at 4 degrees Celsius, not at 0 degrees Celsius. So again, if we go back over to a little made up, where's the pen? Here it is. If we have a little made up column of water in the ocean, then, it's moving kind of slowly. The stuff, oops, that's not supposed to happen. The stuff down at the bottom is going to be at 4 degrees. The stuff up near the top is going to be, at 0 degrees. Here's what I'm trying to convey. This stuff up here is going to be at 0 degrees Celsius, and that's not supposed to happen. So I'll just stop trying to do that. And let's keep going. Fresh water is densest at 4 degrees Celsius, and as a result, ice floats. If fresh water was most dense at 0 degrees Celsius, I guess the ice would sink. Anyway, so ice floats. All right. It's important for driving the climate to understand what happens when seawater freezes. And so when seawater freezes to form ice, it's only the freshwater part that actually freezes out to form ice. All right. And as a result, something has to happen to the salts. So you have salt water, it freezes, the freshwater part turns to ice, and the salts are left behind, which means that the ocean water left behind after this freezing process, the ocean water left behind is saltier. Okay, saltier, and as we saw, heavier. I'm going to have to get this thing to work properly. Saltier and heavier, right? And therefore it sinks. Okay, the cold, salty water sinks because it's heavier and denser. And as we'll see in one or two slides down, this is an important driver of the circulation of the oceans. All right, let's take a look at figure 2.2 in the book to see what the vertical structure of the ocean looks like. And as luck would have it, I don't have figure 2 available to show you, so I'm going to do a truly fabulous rendition of what it looks like. So along this axis, we have temperature, okay, and then down the vertical axis, and I swear I'm going to get better at this, is depth in the ocean. So this is the top of the ocean. Here you are swimming, okay, and everything down there is below you. And what we're going to graph out is how the density of the atmosphere varies with depth. So let's start out with what happens at high latitudes. Okay, so at high latitudes, the ocean is so cold that basically the density doesn't vary with depth. The atmosphere, not the atmosphere, the ocean is just cold and dense all the way down. Then in the tropics, let's go with red for the tropics. Starting at the surface, the ocean is warm, and then it gets colder, and then at some depth you get to basically the same temperature as at high latitudes. So this is in the low latitudes. Okay, so you see that the ocean surface is warm and it's cold at some depth, and then in between there's something interesting. Let's go with green for this thing interesting. In this kind of region here, there's something interesting going on, and what's going on is that the density is decreasing rapidly as we sink down through the ocean. So that's a big density gradient, and we have a name for that. When it's the ocean, we call it, when it's temperature, we call it the thermocline. And when we're talking about density, we call it the pycnocline. So let's look at some words here. The maximum density gradient layer is called the thermocline when temperatures fall off with depth, and it's the pycnocline when you're talking about density changing. The two are a little bit synonymous, temperature and density. Okay, this is the equivalent of an inversion. You may not know this, but in the San Francisco Bay Area, there's a strong temperature inversion, so temperatures get warmer as you go up under the right conditions, and that inversion prevents mixing. And that's the important thing about the pycnocline or the thermocline here, is that it prevents mixing between the upper ocean layers and the deep ocean layers. Okay, let's see, inhibits vertical mixing. The top layer of the ocean is called the mixed layer. That's the bit up here. It's well mixed in properties. When it rains on that layer, the salinity decreases, and at the same time when you have evaporation, the salinity increases. That should be fairly obvious, hopefully. If we go back to blue here, if you've got rain falling on the ocean, well, obviously it's going to dilute the saltiness of the upper ocean and make it less salty. But then on the other hand, in some areas, for example, the subtropical oceans where there isn't much cloud cover, when you have evaporation, that will take away fresh water from the upper layers and increase the saltiness. Now there's a concept we can think about called water masses. Water masses are large masses of air that maintain their temperature and salinity as they move around in the ocean, kind of like air masses in the atmosphere. You should be familiar with the idea of air masses in the atmosphere: hot, dry air, warm, humid air, and so forth. And the thing about air masses is that we can use those to trace air motions in the atmosphere, and with water masses, you can use water masses to trace motions within the ocean. So let's talk about some of the more well-known water masses that we talk about. And the first one is in the Atlantic Ocean, and that is Antarctic bottom water. As the name suggests, it's near the Antarctic and it's at the bottom of the ocean. And we use the abbreviation AABW, Antarctic bottom water, to abbreviate this. Antarctic bottom water is very cold and very dense and salty, and that's that business of ice forms at the surface, the salts are rejected, the remaining seawater is very cold and very salty and very dense, and so it sinks to the bottom, and when this happens in the region of the Antarctic, you get Antarctic bottom water. Forms as ice forms, just like I told you. Eventually it sinks. Having formed at the surface, it sinks to form bottom water. Okay? Now, if we think about the North Atlantic, and there's a figure in a minute we could look at about this. In the North Atlantic, the same thing happens, but now we're talking about North Atlantic deep water. Also cold and dense. Turns out to be not quite as cold as in the Antarctic, and this forms around the Arctic. So we got a lot of cold, dense water. We also have outflow from the Mediterranean, and that water is warm and salty. I'll show you a map in a minute to explain why it's warm and salty. Figure 2.8, let's see if we can find that to see how these are organized. Okay, here's figure 2.8, running from the South Pole at the left to the North Pole at the right. The top of the figure represents the surface of the ocean, and way down here is the bottom. And this gray stuff indicates solid rock. Okay, so what do we have? We have the formation of Antarctic bottom water up around the South Pole. And as the water gets cold and dense, it sinks way down to the bottom of the ocean. So presumably, I'm not completely sure of this, but presumably the Titanic sitting on the bottom of the ocean somewhere is sitting in Antarctic bottom water. Water that formed up here and then sunk down. North Atlantic deep water. Cold and dense, it sinks, but it isn't quite as cold, so the densest water's at the bottom, and then the North Atlantic deep water is above that. Way up at the top is the nice warm surface water that we're used to swimming in, and in between is something called intermediate water. And how do these move around in the oceans? Well, here you go. Here's a map. This is figure 2.7. This gray area here and this gray area here are the two primary formation regions for Antarctic bottom water. So as ice forms in this region, the cold water sinks down. And then as you can see, there's a general west to east flow of that deep cold water. Some of it also spreads out into the Indian Ocean, spreads out even further into the northern Pacific Ocean. And then in the North Atlantic, you have the formation of the North Atlantic deep water. It sinks and flows southward through the Atlantic into the southern hemisphere and then merges with the Antarctic deep water. Here's the I can tell you from personal experience that the water there is nice and warm, and so there's a lot of evaporation, and so the water that's left behind is warm and salty, and that comes pouring out here from the Straits of Gibraltar into the surface of the Atlantic, warm and salty. And then the red curves here represent the surface water. So here is the Gulf Current going up the surface along the east coast of the United States up over towards northern Europe. I got a few notes here about the circulation from figure 2.7. The whole thing is called the thermohaline circulation, this thing here, and you should be familiar with that phraseology. So that refers to the overall circulation of ocean water across the planet. It's not hugely important for day-to-day weather, but it is hugely important for understanding climate and climate change. And here's a Wikipedia link if you want to read more about it. Sinking at high latitudes around the polar ice caps, flow away from the poles very deep in the ocean. The water has to eventually warm up and rise somewhere else, and there's just a giant overturning circulation. And this is important and also interesting. How much time is involved in getting this circulation of water around the planet? Answer: hundreds of years. I think that's interesting. Now what's next? Let's take a look at figure 2.4. Figure 2.4, this shows you the circulation of surface waters. This is something that you should already be fairly familiar with. For us in the Pacific, you have a overall clockwise circulation in the North Pacific. Poleward flow just off of the Japanese coast, and equatorward flow off our coast. Same in the Atlantic, poleward flow off the coast of North America, southward flow off the coast of Spain and West Africa. Get the opposite in the South Atlantic. Now it's an anti-clockwise, counterclockwise circulation, and the same in the South Pacific. So along the equator you have a strong flow of ocean water to the west, especially in the Pacific, less so in the Atlantic. There's a word I want you to be familiar with. That's gyre. Gyre refers to these big overturning circulations in the ocean, the horizontal circulations. Things like this. Things like this in the Atlantic. This is called a gyre. Now something else that we're interested in the ocean are sea surface temperatures. There's a figure in the book 211, but why look at an old figure in the book when we can look at the current sea surface temperatures? So let's talk about sea surface temperatures. We often use this acronym SST for sea surface temperature. Okay. SST, sea surface temperature. The main thing that drives the sea surface temperature, at least initially, is the radiative heating coming in from the sun, and we'll be talking about that a little bit later on. We're going to talk in a minute about upwelling, but I want to move on to talk about sea surface temperatures, and we'll come back to this slide, but let's have a look at today's sea surface temperatures. Sea surface temperatures for today, July 25th, 2013. When you look at a figure like this, you want to always look and see what the color bar looks like. The color bar down here is down here. The bright reds are 90 degrees Fahrenheit. Between blue and pale green is about 65 Fahrenheit, and dark blue is ice. So I'll let you look at this for yourselves. As you can see, it's really warm along the equator, nice and warm through the Mediterranean, very warm in the western Pacific. A couple of really interesting things to notice. One here off the coast of California is this blue intrusion. So if you imagine that you're sailing along at this latitude towards California, warm, 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 cold. Very cold off the coast of California. Also a little cool off the coast of northwest Spain. Likewise, off the west coast of South Africa, cool. And off the west coast of South America, cool. That's very standard and it's well understood, and we'll talk about it in a minute. The other thing that we like to talk about are sea surface temperature anomalies. That is deviations from average. And here is the most recent sea surface temperature anomaly. And you can see the URL at the top here. Again, you want to look at the color bar at the bottom to see what kind of things we're talking about. Let's see, green, light blue, and purple colors represent sea surface temperatures that are below average. So there's one that jumps out of the page, I think, really quickly, and that's in the eastern Pacific, eastern equatorial Pacific, and off the coast of South America. It's over 2 degrees Celsius below average in here. This is the region where El Niño begins. El Niño is characterized by sea surface temperatures warmer than average, and so this is the opposite. So this might be a signature of a La Niña underway at the moment. And then if we look at the rest of, especially in the northern hemisphere, we see a lot of temperatures that are above average. The North Atlantic, quite a lot warmer than average. Northwest and north central Pacific, and interestingly, along the coast of Siberia, the Bering Straits, nice and toasty, 2 to 3 degrees Celsius warmer than average. Let's finish up this section by looking at the phenomenon of upwelling, which accounts for those cold temperatures off the coast of California. The upwelling is due to something called the Ekman effect. Okay, after somebody called Ekman, roughly 100 years ago, who did the math to explain this. Let's see how this works, and I have a couple of slides here to explain the Ekman effect. Okay, here's one of them. I don't know if I can draw with the pen on this or not. Yes, I can. All right. Well, maybe I sort of can. So here's how the Ekman effect works. You can see with this dark blue arrow, we have an indication of what the wind direction looks like. Due to the Ekman effect, this is the air motions at the top of the ocean. In the ocean itself, the motions are to the right of the wind, and the further down you get into the ocean, the more to the right the flow is. Okay, so the surface current will be to an angle of the wind, and the current below is to an even larger angle. This is called the Ekman spiral, and this big gray arrow here indicates that the net ocean water transport is not in the direction you would expect. You'd expect that the surface wind is driving flow, in this case, in that direction, but actually because of the Ekman effect, the driving is to the right. So when we put this together with the California topography, this is what we get. So going from left to right, this is west to east. Here's the Pacific Ocean, here's the Coast Range. And one of the things we know about our climatology here is that we always get winds parallel to the ocean, roughly. So along the California coast, which is oriented northwest, southeast, we get winds from the northwest. But because of the Ekman effect, the ocean water is driven in an offshore direction. But that can't be because there is no ocean over here to provide water to flow offshore. So the only way to resolve that is that cold water from the bottom of the ocean gets basically sucked up to provide a source for this water that's flowing offshore. And that's the process of upwelling. So again, the wind blows parallel to the coast. That drives an ocean circulation because of the Ekman spiral ocean flow is directed offshore, and to replace the water that's flowing offshore, you have cold, upwelling water. It's nutrient rich, so it's good for the fisheries, but it's not good for swimming. Okay, I think that just about wraps up this section. You can look at these slides yourselves. And now it's time to move on to something else.